Okay, let's have a look at balance. An in-plane balancing of rotating masses is what we're going to look at here today. Okay. Now, there's a little bit of prerequisite work here to be aware of, something you may have covered before. Some of you have done A-level studies, you probably have covered before, but we don't cover this on level 3 mechanical principles. So I'm just going to mention this to you. It's not a big deal here. It's just a technique, a concept almost, that we need to be aware of, that we're going to apply today. You may have heard of things called centrifugal forces. That's something that is sort of often used in general parlance. People talk about centrifugal effects. But actually, centrifugal effects are actually fictitious. There's no such thing as a centrifugal force, even though most people may have heard of it. What we actually have when we're rotating objects in a circle, as shown in this diagram here, we're rotating a mass, the M, in a circle. We don't actually have any centrifugal forces in the system. We actually have centripetal forces and centripetal accelerations. So in the diagram shown here, you've actually got a mass on the end of a piece of string or a rod, length r here, going in a circle. And as it rotates in that circle, that mass is always subject to an inward acceleration, because if you look at the velocities, just highlight the velocities here, there's a velocity vector here, it's a linear velocity of course, at that particular instance in time, that mass has that linear velocity, and then if we take another instance, an angle theta, it's moved through, and we look at the linear velocity at this point here where the mass is, the linear velocity has changed its direction. Now if you've got a change in direction of velocity, the magnitude is the same here, we're rotating at a constant angular velocity, but we've got a change in linear velocity, then you have to have, for that to occur, an acceleration. And it can be shown that that acceleration is inward to the pivot point here. So that's an acceleration going inwards, and that acceleration is changing the direction of the velocity. It's not changing its magnitude, but it's changed the direction. And that inward acceleration is actually given a name. It's called the centripetal acceleration. You'll see in a minute there's a formula for centripetal acceleration. So whenever you rotate anything in a circle, whatever it is, think of a conker on the end of a string that you're whizzing around your head. What you're doing to make that conker go in a circle, you're always pulling inwards. There's always an inward force, and that's because if you've got an acceleration going inwards, then from Newton's second law of motion, if you've got an acceleration, you must have a force. Remember, the force equals mass times acceleration in our level 3 work. Well, if you've got the acceleration shown because you've got a change in velocity, then you have to have the accompanying force shown. So F equals ma, that basic equation for Newton's second law we've used before, is applicable in this case when you analyse something that's rotating in a circle. There is always an inward acceleration, so there's always an inward force. And they call that force a centripetal force. Now, sometimes Newton's second law is not written as F is equal to ma. It's actually written as F minus ma equals to 0, which sounds a subtle change. But often engineers use this concept of what's called static balance to analyse problems. Engineers like static balance. They like things to be in equilibrium. If you're ever analysing structures like we'll be doing in the next part of the syllabus, we'll always be using Newton's first law, because Newton's first law assumes everything's in equilibrium. But when you've got a rotating mass, you've got something that's accelerating, that's subject to Newton's second law, and that's not a balanced situation. There is an outer balance force required to give the acceleration. But we can write the second law, as I said, F equals ma, in terms of the F minus ma equals to 0. And it's called D'Alembert's principle in some textbooks. And this negative ma is actually like a fictitious force that we're using to bring the system into static equilibrium. It doesn't exist really, but it's something we can use as a concept to give us this static balance which engineers like to use. And the reason I mention this is because in a minute we're going to use this kind of principle of this fictitious force when we consider centrifugal forces. Just looking at some formulae here, don't get too overwhelmed by all the formulas shown on. You only need one of them today. I'm just showing you here that it can be derived that the centripetal acceleration, going back to our diagram on the previous page, the inward seeking acceleration, can be proved to be A is equal to omega squared r. Little proof behind that, which I'm ignoring here. The omega would be the angular velocity, like we've seen angular velocity used in other topic areas. R is the radius of the rotation in this case, and A is linear velocity. So that's the centripetal acceleration written in terms of angular velocity. It can also be written in terms of linear velocity. If you remember this relationship, omega is equal to the linear velocity divided by the radius. That's a standard relationship we used before. V is equal to omega r. In other words, we can actually write that centripetal acceleration above in terms of the linear velocity as v squared upon r. Just another way of writing the centripetal acceleration. Now, if we now apply that into Newton's second law, of course, is equal to force is equal to mass times acceleration, then the acceleration above the omega squared r becomes the A in the equation, and we end up with this formula of F equals m omega squared r, and that's called a centripetal force. Okay, that's an inward seeking force. That's written in terms of the omega, so that's in terms of angular velocity, and you can, if you want to, write it in terms of linear velocity as F is equal to m v squared upon r. It's the same force there, just written in terms of linear velocity there. Okay, so that's the force that can be shown to be always pulling inwards when you're rotating anything in a circle, this F equals m omega squared r formula. Now, what we're going to use is this concept of centrifugal forces. Okay, if you think of the little diagram they're showing you, there's this shot putter there swinging the shot put around in a circle. To do that, what that shot putter has to do is always pull in. It always has to be pulling in with a centripetal force. So the inward seeking force, it's sometimes called, is this centripetal force. That's the force he actually applies to the shot put there. But there could be considered an outward force called the centrifugal force, equal and opposite to the centripetal force. Okay, and some textbooks refer to this as Newton's third law, the action in reaction. It is just a concept, though. There is no force pulling outwards. There never was a force pulling outwards. There is no centrifugal force. But it's a concept that brings dynamic situations into static equilibrium, as shown in this sort of diagram at the bottom here. We've got the centripetal force, is the inward seeking force here. And we're just assuming that there's this outward force of the centrifugal force, equal and opposite, bringing it into static balance. It's just a concept engineers like to use, and we're going to use it in the analysis of the balancing of rotating masses here. So I can also state my centrifugal force as the m omega squared r. Okay, that's the outward force, if you like. And that's the only form we need to be aware of. All what I'm discussing here, it's really the formula here, the m omega squared r formula you need to be aware of. I've just written it there in two formats, one in terms of linear velocity v and one in terms of angular velocity omega, but it's often this first one we need to use in the calculations. So that's just a bit of background. You'll see we'll use that formula later on to help us analyse these rotating masses that we're going to consider. And again, you just sort of illustrations of showing you where you feel these kind of forces. If you're on a wall of these wall of death things, been on one of those years and years ago when I was a bit younger, you get, as I spin it around, you get flung to the wall, and it feels like you're being flung out through the wall, but in actual fact, you're not being flung out at all. You're just being pushed around in a circle. There's actually an inward force from the wall on you, keeping you in a circular motion. If that force wasn't there, you would fly off in a tangential direction. So again, there is only a centripetal force applied to you, even though it feels like to you, because of your inertia effect, it feels like you're subject to a centrifugal force, but there's no such thing there. So it's an interesting concept there. That's all it is, really. Examples for the balances of in-plane masses include flywheels. We could have components bolted to a face plate of a lathe. It's not balanced, might need to balance it. And we could also have things like aircraft propeller blades, for example. Sometimes they can be out of balance and they need balancing. So it's those kind of objects that you'll see is sort of the context, some of the questions that we're going to be reviewing here, okay? I'm going to start off with something very basic, just to give you an idea of the sort of balances principle of moments approach. We're going to use that initially, and then we're going to look at rotating masses with angular velocities. So all I've got here is a disk, if you like, here, and it's got two masses on it, and they've obviously converted the masses here in terms of weight forces, because they're saying that the mass here gives a weight force of 50 newtons, and then the mass over here gives a weight force of 25 newtons when subject to gravitational acceleration. We've got the distance of this 50 Newton force from the centre of rotation is 100 millimeters, and we're asked to find in this particular case what's the distance of the 25 Newton force from the origin. We're taking moments, of course, about the origin here in the middle here. Now, you've covered this in your previous level 3 work. We would just apply the principle of moments here, and the anti-clockwise moments would equal the clockwise moments. If we want equilibrium or balance, then the anti-clockwise moments equals the clockwise moments, and we would just go through the process of doing the calculation here. So very straightforward little calculation. It would be anti-clockwise moment would be the 50 Newton force multiplied by, I'm using millimeters in this particular example, so 50 newtons multiplied by 100 millimeters. That would be the anti-clockwise effect here from that force times distance, and that's balanced by the clockwise moment. In this case, that would be 25 newtons multiplied by whatever the distance L is. So 25 newtons applied here, and then distance L here. Just the principle of moments. I want to balance that in a rotational sense about the origin. Don't forget, we always take moments about a point, so the origin is where we're taking moments about here. I would just divide the 5,000 there by the 25 to get 200 millimeters. 200 millimeters would be the lengths that we're looking at in that particular case. Okay, that's a basic balancing exercise, but that's kind of the principle on what we're going to look at as we move through the little topic areas. All right, so that's just a little illustration of very elementary balancing. So balancing of rotating masses. So when components are out of balance, they have an in-service effect that can be severe. We don't want propeller blades being out of balance, for example, but anything's out of balance, it causes vibration effect. It can just be a situation where we get a poor surface finish on a component, for example, because the machine's out of balance, or a component's out of balance on the chuck face or whatever. So we want to try and avoid these out of balance effects as best we can. The concept of inertia as applied to rotational systems is familiar to you. You may have studied before angular kinetic energy or Newton's laws of motion. We've come across the kind of rotational masses and the inertia effects associated with them. So inertia forces and accelerations occur in all rotational machinery, and these forces have to be accounted for, and then the designer or stress engineer has to sort of design them out, balance them out as such. And that's what we're going to do ultimately. We're going to find what are the out of balance forces in our particular situation, and we're going to try and counteract them by applying a mass at a distance within the system that we're considering. You'll see that in the examples. These are typical examples, some of which we'll consider, where we're required to balance our objects. So lathe faceplates, grinding wheels, car wheels, crankshaft, electric motor rotors. I remember that very clearly. It's this kind of thing here. Electric motor rotors, my days working on electric motors, I used to have a balancing machine to balance these rotors. This is a rotor here. And you can't just see it very clearly, but those little pegs there, little pegs that are they're part of the casting. Actually, it was aluminium casting, and those pegs are where they would put actually steel washers. They would put steel washers on the pegs, and then they'd bang the aluminium spigots and flatten them to tighten the washers on. And that's how they used to balance the rotors, because they had to be balanced before they could go into the electric motor itself. So balanced electric motors, turbine rotors, aircraft propellers we mentioned, helicopter blades. It goes on and goes on. So let's look at static balancing. Okay, we're going to sort of build up to dynamic balancing. So static balancing, and again, all these masses are in the same plane. Okay, so let's consider a stationary shaft here. So this is supposed to be the shaft, such you might find in a jet engine, on which we have masses. And for a jet engine, that would be rows of compressor blades, rows of turbine blades, that kind of thing, all mounted on this shaft. The shaft is said to be in static balance if for the off-center masses there is no resultant force in any direction due to the weights of the masses. So the algebraic sum of the turning moments about the shaft axis is 0. So what we're trying to say here is these forces, I'm showing arrows there, for these masses, I've got a mass 1 and multiply that by gravitational acceleration. That would be for like force 1 acting down. I've got mass 2 here. Multiply mass 2 by gravitational acceleration. I get like force 2 acting down. So it goes on for 3 and 4. What it's trying to say is the effect of those forces times distances about the origin, the shaft in this case, must be 0. In other words, our clockwise and anti-clockwise moments must balance, is what they're trying to say there, if that is going to be in static equilibrium. So considering the geometry here about the origin, we're always taking moments about the centre of rotation, all the exercises we're going to do. So for equilibrium, going back to that concept of equilibrium, the moments, the clockwise, anti-clockwise moments, must equal to 0 about any point for equilibrium. And we're taking moments about the origin here. And I've said here that anti-clockwise moments are positive. It doesn't matter whether you take clockwise or anti-clockwise positive, but I've got anti-clockwise moments is positive. So let's see how they devise this first equation. It's quite a lengthy equation here, but it's something we can build up from the diagram above. Let's consider mass 1, okay? So I've got a mass 1 multiplied by gravitational acceleration. That will give me a force, and I'm showing the force that's due to that mass here. Right? So there's my force acting down. I'm trying to show that over here on this diagram over here as well. Now what we do when we consider moments, don't forget, it's always the force multiplied by the perpendicular distance to the point of rotation. So if this is my force, and I do my line of action to that horizontal, my perpendicular distance from the origin is this distance across here. That would be the perpendicular distance, all right? So my force, m1g in this case, multiplied by this blue distance here, would be the anti-clockwise moments of the m1 mass about the origin. And I've just tried to show the geometry over here. It's just basic trig here in a little sketch here. So there's my hypotenuse of my triangle, if you like. R1 is the hypotenuse of the triangle. So I've got the hypotenuse given to me, I've got the angle given to me, I'm trying to find the adjacent side. That would be the cos function, okay? That's just really basic trig, and that would be the x term here. The x value would be that line across there. Okay, so multiplying my force, my m1g, multiplied by x, which is the r cos theta, I get this first term in our series. Okay, it's positive because the effect of that moment about the origin, of course, is going in an anti-clockwise sense. So that's why it's a positive. I said anti-clockwise is positive. Similar process for M2, exactly the same process. M2 times G would be the force, and multiply this time by the R2 cos theta 2. That again is positive, so that's my second anti-clockwise moment. And then we do the same for M3s and M4s, but they're negative here because, of course, they're going in a clockwise sense, so they're going against my sign convention. But the same process there. It's again the force multiplied by the perpendicular distance, the force multiplied by the perpendicular distance. All right. So that's where that equation is derived from. It's just basic trig there, and working out moments about the origin. Now, as G is constant in all the terms there, we can simply ignore the G. I can easily cancel G because every term that has a G. So I could divide throughout by my gravitational acceleration, divide both sides by gravitational acceleration. And I can write the equation as shown below in this line here. Okay, so this is the equation above, just simplified without the G's. And it equals to 0 for equilibrium. So equation 1 in the bolded box there is just a short form of above. It's just saying summate all the masses times their respective radii, multiply it by the cos of the respective angle. Summate all of those and equate them to 0 for static equilibrium. There's nothing really new in that. If you look at level 3 work we did years ago, we did balancing of beams, you might remember. We did use that same kind of principle. So that's equation 1, little equation for us to use. Now what we're going to do is exercise 1S. So I'm going to try and talk you through this. I'm going to try and give you a structure here. So exercise 1S, it wants us to consider the 3 masses that are shown in the sketch. They're all located in the same plane. So it's Inplane-Balancing we're looking at. And we've got to calculate what mass Z do we need to achieve the static balance. So in other words, what's the mass we need here that will give us rotational balance, that will keep that system in equilibrium about the center position there. Again, we're always going about the origin, about that origin there. Okay, now it gives a little table there with all the information given. Fortunately, not all questions are quite as explicit as this. You have to extract the information, but they've given us a table there. We know that the X mass In this case, x is given as 3 kilograms. So we've got the 3 kilograms, we've got the radius. So Rx would be this value here. And we've got the y is 5 kilograms at a particular radius. So we've got the y is 5 kilograms. We've got that radius given to us. But what we don't know in this case, don't know mass m, we don't know what that one's going to be. But we have got the radius given for the radius of the mass z there. Right, so we're trying to find in this case the mass of z in our diagram. Now, what I'd like you to do first of all is draw a little table for yourself. Right, you're going to develop the solution in your notes here. I know we're repeating the information in the question, but you'll find in the other questions they won't have the information explicitly here. And what you're going to do particularly is calculate the MR value. This column here, all the other information you can get from the table given in the question, but the MR value, the mass times the radius in kilograms meters. Notice we're always using meters here. I want you to just work out that table for me if you would. All right, so we worked out the MR value. Now what I'm going to do next in your solution, sort of next little table, and we're going to work out the MR cos theta value. So we're going back to that equation 1 we derived on our previous slide. And I just want you to work out the MR cos theta value for x and for y. And that will effectively give us the out of balance you'll see in a moment. And at the bottom, summate the terms. So that 1.2937, that is the out of balance moment in this case. Sometimes it's written as MROB in some textbooks, and that's 1.2937. And kilogram meters, of course, is the unit. Now what we've got to do is to decide, well, what's the value of z going to be, the mass in this case, because that's what the question wants us to do. We've got the radius, we know what radius to put the mass on, but we don't know what the mass is itself. The mass z multiplied by the radius of the z, mass z, that's equal to our out of balance, our MR out of balance. And we've got to find mz. So can I ask you just to simply rearrange the equation to find mz, it's mz we're trying to find here, and then put the figures in and calculate the mass. And my mass, according to me, is 9 kilograms. 9 kilograms is the mass we're looking for there. All right. Now, just to show you this. The configuration we're given in the question shown at the top of the page, we're going to add the 9 kilograms to z, and we now know that will balance the system about the shaft, the rotating shaft in the middle. We know it's balanced about that. I'm doing red here. That's the rotational point we're looking at, the shaft. And we know it's balanced with that 9 kilograms. But that's only balanced in that position. So only static balance has been achieved at that one orientation, due to the effect, gravitational effect. So gravitational effect on that situation at the top of the slide there, that is in balance. But if we were to rotate it through 90 degrees, so an anti-clockwise here on this diagram here, you can clearly see now that that will not be balanced. It's clearly seen that it's still an out of balance here due to the effect of gravity again. So in other words, the weight force or the force associated with x, mass x, would go straight through the center, so that would be okay, and the weight force of the 9 kilo mass, that goes straight through the center we're considering, so that's okay. But of course the weight force of y now will be offset by some perpendicular distance, or x there, so of course the whole system will now want to rotate in the anti-clockwise direction. So that's not balanced. So you can see with the process we've gone through so far, yes, we've balanced it for one instance, but we changed its position and we no longer balanced it. So that's called static balance. It's static balancing in that particular instance. What we need to be able to do is balance our rotating masses for any orientation of the system. And that's where the dynamic balancing comes into play. So we're going to move into dynamic balancing of our masses. Again, all in the same plane. Nothing is out of plane. It's all in a two-dimensional plane here. So if a shaft is considered rotating about the point O, and each mass experiences a centripetal acceleration because it's rotating now, we know that the centripetal force is always directed inwards towards the origin. We know we have to have a centripetal force if we want circular motion. Each mass in this case will experience this centripetal force associated with it as it rotates, because it's always being pulled inwards as it rotates around the circle. But if we want to use this concept of equilibrium, we can then consider a centrifugal force of equal magnitude but opposite direction, acting outwards. So this is this balancing effect we're going to use. So you'll see in the questions we're going to look at now, we're going to consider the F equals m omega squared r equation. That's basically your centripetal force if you're considering the inward seeking force, or if you're considering the equal and opposite force, that's the centrifugal force acting outwards. And what we're going to do is consider the sum of the centrifugal forces in our calculations, because they must equal to 0 if we have a balanced system that we're analysing. And again, this idea of bringing things into balance, engineers like that concept. It makes the analysis slightly easier when you're considering that we've got equilibrium of the forces, to the left balances the forces to the right, the forces up balances the forces down. That's a nice concept engineers like to use. So you'll see that formula will crop up in what we're going to look at now. We're going to start by considering a dynamic balance of just two masses, and they're diametrically opposite each other, again in the same plane. So we've got in this our diagram, we've got a mass originally, it's some radius, okay, so it's obviously an outer balance there. So when it rotates, you'll feel this centrifugal force, dare I say, acting outwards. What we're going to try and do is balance that outward force by an equal and opposite force by putting a mass, it's some radius, diametrically opposite to the original mass. So they've called the original mass little m and the original radius little r, and in this notation they've got the balancing mass is big M and the balancing radius is capital R in this case, okay? Alright, so in this case we've got our balancing mass directly opposite the out of balance mass. So if we want to apply this concept of equilibrium, then we know that the force m omega squared r, lowercase, which is the out of balance mass we've got, is going to be reacted by the centrifugal force of the m omega squared r using capital letters there. They're equal and opposite, okay? What they've done here is obviously cancelled the omegas, because the omega is common to both sides, just like the g was in the previous equation when we're looking at gravitational effects. The angular velocity is common to both sides of the equation. You can delete the omega squared value. So their equation 3 is simply mr, the capital M, capital R, which are balancing mass, is equal to the original out of balance situation we've got for equation 3. So we can cancel the omega squares because everything's rotating at the same angular velocity here. So this is just a very simple scenario. It is dynamic balancing there. We are talking about something moving with angular velocity here. So we have these centrifugal forces to consider. But it's only two masses and they're diametrically opposite to each other. Let's have a little look at this question. Just asking us to calculate the centrifugal force here together. I'll outline this for you. Problem 1I. So a single stage turbine has 140 blades. Each has a mass of 180 grams. Need to be careful with that. And a mean radius of 300 millimeters. We've got to calculate the resultant force if a single blade comes off when the turbine speed is 11,000 revs per minute. So just need to be careful with the units given here. Very straightforward calculation. It just wants us to find the centrifugal force here, but some of the units are a little bit dodgy, so we need to be careful of those. So taking information in the question, we've got an angular velocity given in the question, and that's given us 11,000 RPM. I normally use the capital omegas for my angular velocities, 11,000 RPM. But don't forget, we cannot use that in the calculation. I know in some of the gear calculators we have used things in RPMs, but for this work we cannot do that. So we're going to have to calculate that in terms of the radians per second, omega. So I'm going to let you do that. I'll get you appropriate conversion in a moment to calculate that one. And then we have to work out the centrifugal force. Now we need to be careful here because of the unit of the mass. I notice the mass is in grams there, so perhaps I'll write that down first of all. The mass of a blade, we need to put that straight into kilograms, so 0.18 kilograms. We've got to be careful with the radius, that's in millimeters. I'm going to go to meters. It's given as 300, so 0.3 meters. And then we've got to calculate the centrifugal force, call it F. And that's the m omega squared r formula. So I'm going to let you do the number crunching on this, if you would. Just popping one out. So my 11,000 RPM, convert that into radians per second. I get 1,152 rads per second. Yeah, so my mass must be in kilograms, 0.18 kilograms. And my radius needs to be in meters. That's no exceptions there. Always use those units. I've got it in terms of kilonewtons there, but 71,650 newtons is fine. Problem 2. Got a large flywheel of mass 0.2 ton. Has a centre of mass offset by 9 millimeters. At what radius should a mass of 10 kilograms be placed so that the flywheel is located in dynamic balance here? So we've got to consider it as being rotating here. So again, I'm going to try and get you engaged with this. Take the information from the question. So a large flywheel has a mass of 0.2 tons. Put that into kilograms straight away there. The centre of mass is offset by 9 millimeters. And again, be very careful with the units here. I've put my offset straight into meters. What radius should a 10 kilogram mass be placed? So we're given a 10 kilogram mass to balance it if the flywheel is in dynamic balance. Okay, so going back to equation, it was 3 in our notes. You've got these masses that are diametrically opposite to each other. So you're going to have, if I call it big M multiplied by big R, so the balancing mass multiplied by the balancing radius must equal to the mass of the flywheel. This little m I've got here multiplied by the radius of the balance of the flywheel. Alright, so that's the equation you're going to use, and you're going to rearrange this. You've got to find R. So again, I'll let you put the numbers in if you will, and work out what the radius is going to be. It looks like it's 0.18 meters. That's just given in millimeters there, but it work out in 0.18 meters. You can get away in this particular question of using millimeters if they want the answer in millimeters, but be very careful. I would always encourage you to go to meters in most instances. There's my solution for problem 2i. Okay, so for dynamic balance, my balancing mass multiplied by the balancing radius must equal to the mass of the flywheel times the off-center distance r. And I'm just simply going to rearrange the equation for r. So my r in this case is 0.18 meters because I used the 0.009 meters in my calculations, but the answer on the sheet is actually given in millimeters in this case. So that equation that we're showing there, the mr equals the mr, that only works when you've got these two masses and they're diametrically opposite each other. So we're looking now at dynamic balancing of multiple masses, and of course they're still in the same plane here. So the diagram you're seeing here is quite similar actually to the diagram we had a few slides previously when we were looking at static balancing. But when we're looking at static balancing, we're just considering the effect of gravitational acceleration on the masses. The difference here is that this system now is being rotated with an angular velocity, I've called it omega here, in the clockwise direction there. And as the system's rotating, we now have centrifugal forces pulling outwards at each of the mass locations. As the lines of action of the respective centrifugal forces all act through the same point, labelled O here, we only need to consider a force balance and not a moment balance in this situation. Thus, each of the centrifugal forces were resolved into their horizontal and vertical components and summate them. So in this case, we're resolving into the horizontal plane. We find we end up with an expression that has to be satisfied for dynamic equilibrium. So what we've got here, if you look at this equation, it's quite similar to what we saw previously when we were doing static balancing. That had mg r cos theta. This has got m omega squared r cos theta, but it looks a very similar format here. So what we're doing here is resolving these forces into their x and y components, as sort of shown on this diagram here, sort of a horizontal component and then a vertical component. So those are centrifugal forces, m over squared r is there. And we're just resolving into horizontal and vertical components as shown there in a little sketch. And what we're doing is summating all the horizontal components of the centrifugal force to give us equation 4a, they've called it there. So 4a, the mr cos theta, is equation 4a. What they've done is cancelled out the omega squareds from each of the terms, because of course omega squared is common to all the terms, that all the masses are subject to the omega squared term. So they can just be cancelled out. And what you notice now is that equation here, if I just highlight it, the summation of the mr cos theta is equal to 0, equation 4a. You see it's same as that one, equation 1, the mr cos theta. All right. When we did static balancing, the equation we derived was mr cos theta, that was equation 1. And when we do dynamic balancing, what do we get? We get the same equation. So what you can say is when we're dynamic balancing, we're by default static balancing. Okay, we can't say that about static balance. When static balancing, we don't have dynamic balance, but when we're dynamically balancing something, implicitly we've got a static balance, because that is the equation for static balance. If we resolve into the vertical plane, in other words, consider all the m omega squared r's times the sine theta, so this is the vertical component of that particular force there. So if we summate all the m omega squared r sine theta terms, we end up with this equation. Okay, and that equals to 0. And that's balancing in the vertical sense. So we've got a horizontal balance and a vertical balance here for dynamic equilibrium. So we're going to have these two equations that we're now going to apply in our balancing. So what you're seeing there is what we now need to consider in the rest of the analysis there. I'm also going to use in the calculations complex notation. So within all the following calculations, complex notation is going to be used. I'm going to plot them on an Argan diagram. If you remember, Argan diagrams back with our complex numbers had the real axis on the horizontal axis and what we call the j-axis, the imaginary axis, on the vertical axis. And I'm just going to use that notation. I'm really just drawing an XY diagram, that's all I'm doing. But I am going to refer to the j components because they'll be the vertical components of our force balance. Okay, so we're going to employ the Argan diagram in calculating resultant out of balance for the system. So we'll be using a bit of Pythagoras theorem to work out the modulus, resultant if you like, of our x and y forces, and also I'll be calculating the angle theta using the x and y components as shown here. Just very standard Pythagoras theorem and basic trig. Just to work out these angles. We've done this kind of thing before in mathematics at level 4 actually. So this is example 1i. So we've got two masses that revolve together in the same plane, an angular distance of 45 degrees apart. The first mass is given as 3 kilograms, that's located at a radius of 225 millimeters, and the second mass is 5 kilograms, and that's rotated at a radius of 175 millimeters. We've got to determine the out of balance force when the assembly and the system is rotated at 120 RPM. And we've got to find the position, that's the radius, of where to put a 9 kilogram balance mass to eliminate the out of balance from our system. So in this case, we'd have to draw the sketch and take the information from the question, which I'm showing the solution below here. So my little table again, extracting information from the question, my masses, m's, my radii given there. Notice I put them in meters straight away. Working out my MR values, the mass times the radius, and the angles again are given in the question. Now the way I've orientated my diagram, I've put the X mass, I've called it here, which is a 3 kilogram mass, in the horizontal. So that's at 0 degrees, and then the 5 kilogram mass, which is located at a distance of 45 degrees around. I'm showing that here, 45 degrees around. Don't forget with our complex notation, one of the things we do need to remember, which is absolutely essential for our work, is that the positive angle theta is always measured in an anti-clockwise direction from this horizontal here. Always. That's positive theta. Always that way round. So we need to remember that, okay? Okay, so I've extracted the information of the question, draw my little table, which I always encourage you to do. I'd like you to keep the structure of the solution very similar to what I'm showing you here. I just think it's a nice structured solution in this case, and you can apply it to all the questions. All we've done here is worked out the MRs. That was not given in the question. We've worked out the MR values. I've calculated the angular velocity in radians per second. It was given in the question in terms of RPM, 120 RPM, and of course we always must calculate in terms of radians per second, so there's my omega value in terms of radians per second, 12.57. Now here's my MR tables, I sometimes term it, my force values. Not actually force values, you see, because they haven't got the omega squared value in, so not actually forces. We're not actually calculating forces directly here, because we simplified the equation by taking omega squared out. So these are MR values, and they don't have the Newton force associated with them. And you'll notice I've used the complex notation here in the table. That just means that there's J notation, that's all, to show that they're vertical components, that's all. All right, now, unlike the previous table we did when we looked at the initial exercise, we were just considering static balance there, so I only had the one column of the working out the MR cos thetas. In this case, we've got to work out the MR cos thetas and the MR sin theta values, and that's what I'm doing in the table. So for x, the MR value above is 0.675. The angle in my diagram is 0, so multiply it by cos of 0, I get 0.675. In the vertical sense, the MR value is going to be 0.675 multiplied by the sine of angle theta, and of course that will be 0 because sine of 0 is 0. And then I do the same for the y mass. In this case, the MR value above is 0.875. The angle is 45 degrees. It's 45 degrees round here. So I can work out my MR cos theta value, and I just do exactly the same, but for the sine theta value, work out my J value if we want to there. All we do is summate the values, add them up, so adding up my out of balance in the horizontal sense, that's due to the horizontal force components, 1.2937, and then doing the same, adding them up for the vertical components, I called them the J components there. So my out of balance force is going to be MROB, and that's from above the table. It's 1.2937 in the horizontal sense, and I add to that my J, 0.6187 in the vertical sense. I can use Pythagoras theorem to calculate the resultant out of balance force. That's purely Pythagoras theorem there I'm using for the above two x and y values, and my out of balance works out to give me 1.434 kilogram meters. The actual force is going to be the MROB, this value here, multiplied by the omega squared, because don't forget centrifugal forces m omega squared r, but we took the omega squared out when we do the table for simplification. I don't want to keep multiplying everything by omega squared all the time because it's a constant. So we work our out of balance out on the MR values, but if they actually want the actual force, then we've got to multiply it by the omega squared value to get the force. So the actual force that's out of balance is 226 newtons. This is the Argan diagram. It's just an XY diagram, really. It's just that the real numbers are on the horizontal and the imaginary numbers, the J numbers, on the vertical, that's all. So all I've plotted here is 1.294 on the horizontal. On the vertical, I've got my 0.6187 from my tables above, and I've worked out the resultant force with this calculation here. That's the resultant out of balance force, okay? I know it in terms of MR, it's 1.434 kilogram meters. I know it in terms of the actual force, it's 226 newtons. I also need to work out the angle, and this is where you need to be careful with the angles, because we always have to measure our angles positive, as shown in the diagram here, always positive from the horizontal round in an anti-clockwise direction. So as the vector I'm looking at here is in the first quadrant, then of course the angle theta is, as I calculate from my formula of inverse tan function. So again, this is basic trig. That's what I'm doing, okay, that's what it is. And of course the inverse function is used to find the angle theta, tan to negative 1. Notice I used arctan here. That's another way of saying tan to negative 1 of that value. Give me 25.6 degrees. Now that actually is the angle of the out of balance here. We need to be careful. If the out of balance was, say, in this quadrant here, for example, which it will be in some questions, then you need to work out this angle first of all here. I sometimes call it alpha. So you work out alpha from this equation, and then you subtract alpha of 180 degrees to get angle theta. So be careful of that. It depends on where your phasor is, your resultant outer balance is as to how you actually calculate angle thetas, but they always must be measured from the horizontal in an anti-clockwise direction. Okay, so now I've got my outer balance force, I've got my outer balance angle given to me. What we've got to do is balance the mass, and we've got to decide at what radius to put the mass. That's our question here. Okay, so going back to the equation we used previously, our outer balance mass multiplied by our balance radius must be equal to the MROB. So rearranging the outer balance radius is the MROB, calculated above, divided by the balance mass. The MROB appears 1.434, and I'm dividing that by the mass we're adding to the system, which is 9 kilograms. And that gives us a radius of 0.159 meters. So now we know what the radius is where we add the balance mass. Now what we've got to do is find the angle at which we now add the balance mass. So if we want to balance the above force, all right, so don't forget the Argan diagram has shown us the out of balance force here. If we want to balance that, then we need an equal and opposite force here. This would be the balancing force here. Okay, that's what we're trying to calculate. So our equal and opposite force will be an angle of 180 degrees added to the 25.6 degrees. So that's 180 degrees around here, okay, to get the angular position. Because we're not just dealing with two masses now, so it's not diametrically opposite a mass, we're dealing with several masses, so we have to go diametrically opposite the outer balance force. And that's what I'm showing here. That's where the 205.6 angle comes from. Alright, so basically what we've done is put that mass of 9 kilograms here, at this position here, on a radius, which we calculated of 0.15 meters, okay, at the angle of 205.6, and that's degrees there. And that's job done. That's balanced our system in this particular case. And so what you see there is what we've got to do. That's what it's all about for us. We've got to use that approach in all the questions. So just very quickly, exercise 1I. The grinding wheel operating at 1500 meters per minute is out of balance by a 10 gram mass at a radius of 150 millimeters. We've got to calculate the out of balance force that's been induced, okay? And they mentioned the ratio V is equal to omega r, because what they've actually given you in the question is a linear velocity. It's talking in meters per minute, and that's a linear velocity. So you have to calculate, first of all, the meters per minute into meters per second by dividing by 60. So that's now still a linear velocity, 25 meters per second. And then using the V is equal to omega r equation, you can work it out as an angular velocity. And then from there, you can obviously work out your out of balance force m omega squared r. So that was all that question was about. So I'll let you browse that at your own time if you want to. Let's go to exercise 2I, which is more like the example we've been looking at. So exercise 2I, we've got a rotating system, consists of 3 masses, and they very conveniently have tabulated them for us. That's nice. On a rigidly fixed shaft. All the masses can be considered to act in the same transverse plane. Okay, we would assume that anyway, what we're doing. We've got to calculate the magnitude and the direction of a mass required for balance if the mass is to be located at a radius of 500 millimeters from the center of the shaft. So in this particular question, we've got to calculate the mass. In the example that we looked at previously, we have to calculate the radius. We were given a mass to calculate the radius. In this case, they've given us the radius, we've got to calculate the mass. So it's a very, very similar approach to that used in the previous question. So can I get you to engage with this? There's an example blank here. I've drawn my diagram. I encourage you to draw a diagram as well. It's always good to have a visual diagram. I'm just taking information from the question, and I put my masses at this particular angle. So element number 1, or mass number 1, is 6 kilograms. So 6 kilograms, that'd be a radius of 800 millimeters. That'd be 0.8 meters I would use, and that's at 30 degrees. So that's my 30 degrees, just drawing them on the diagram here. And then mass 2, it's 6 kilograms, that's 130 degrees. So 6 kilograms on 130 degrees. And element number 3 is 5 kilograms, that's at 250. Again, notice how I've measured the angles here element number 3, 5 kilograms. That 250, of course, is from here round to here. Notice I put it on diagrams negative 110 because you can measure negative angles if you want to from here. So don't worry, you can use a positive 250. But if you want to measure negative angles, then you can do. They go in a clockwise sense from the horizontal here. Okay, can I get you to work out the MR values? So you might want to construct a little table of the information above with the MR values added in, because you need the MR values, and then see if you can calculate the MR force values in the table I'm showing there. Those two items, my MR values, if you agree with them. So MR values, just picking MR value from the table, MR times the cos of 30, horizontal component, MR times the sine of 30, vertical component. That's my solution. So we're in the first quadrant again, because the angle we calculate from the arctan formula there is the angle we need. As I said, it's not always the angle we need. So if it's in a different quadrant, but it is in this case, that's where it's at fine. Finally, you've got to find the balance mass. We know the balance radius is 0.5 meters, I think, in the question. So rearranging to find the balance mass, I get 5.162 kilograms. And don't forget the angle that we need to put our balance mass at. So we get the 227 from, all right? So, okay. So hopefully you're battening down a bit of the process involved here. What does change is the way the questions are worded. This process will be quite similar, but the questions can be more confusing. Exercise 3I to do in the session. We got a propeller of an aircraft consists of 6 equi-spaced blades, and shown in the sketch. After an in-service operations, the blades are checked for damage. It's found that blade 1 has lost 50 grams, blade 3 has lost 80 grams of its mass, probably due to runway debris, they say. All blades initially had a mass of 500 grams. So if the centres of gravity for blade 1 and 3 are 680 millimeters and 660 millimeters respectively, and all the other blades have a centre of gravity of 700 millimeters, we've got to calculate the balance mass required and the angle at which it must be located if the mass is to be situated at a radius of 0.3 meters. A lot of information there, and this time it's not explicit information. We're not actually given some of the masses. We need to calculate them here. So this is the kind of thing you've got to engage with. The actual process that you'll be going through for solution will be very similar to what you've done in the example in the exercise 2I, so that the process is the same, but now you've got to sort of figure out what exactly are they asking us to do here with all this information that we've got. So I'm going to start you off by sort of thinking through the information given. Extracted the information from the question. So we initially have 6 blades and they're all equi-spaced. So we got our angle 60 degrees for each of the spacing. We know that the original blade mass was 0.5 kilograms. I'm converting all my grams dimensions into kilograms, or my millimeters will go into meters for the calculations, all right? So original blade mass was 500 grams of 0.5 kilograms. Now, after the in-service operations that they've undertaken, we know that blade 1 has lost 50 grams or 0.05 kilograms. So the new mass for blade 1, I've called it M1 there, will simply be 0.5 minus the 0.05. So 0.45 kilograms. That's the mass of blade 1. We're given in the question its radius. So blade 1 radius, we just call it radius gyration, just think of it as the radius. R1 I've called it, is 0.68 meters. So they gave us 680 millimeters in the question. I'm converting that to meters. So that's the new information for blade 1, all right, that got damaged. Let's look at blade 3, which also got damaged. So blade 3 now, that lost 80 grams or 0.08 kilograms. So its new mass, M3 I'm calling that, is 0.5 minus a 0.08, so 0.42 kilograms. And we're given a new radius for blade 3. Its new radius, called R3 here, is 660 millimeters or 0.66 meters. We know that all the other blades, they have a mass of 0.5 kilograms and a propeller radius of gyration of 0.7 meters. Okay, so that's extracting the information from the question. Exercise 3I continued here. There's a note added to the slide. As blades 2 and 5, so 2 and 5 here, are diametrically opposite to each other, they have the same mass and the same radius of gyration, then their respective centrifugal forces oppose each other, and thus they balance each other out. So in other words, the centrifugal force from blade 2 is the same value as the centrifugal force from blade 5. So as they're diametrically opposite each other, there's no need to include them in our calculations because they literally balance each other out. So therefore blades 2 and 5 can be omitted from the analysis. All the other blades have to be considered in the analysis as they have different masses and different radii. So we have to consider blades 1, 3, 4 and 6 in the analysis. Just note for reference, we can actually reduce the number of blades down to 2 if we account for the difference in mass between the diametrically opposing blades, but from a learning perspective I think it's easier at the moment to use the 4 blades as shown in the table. Notice the units used, always use kilograms for masses and meters for radii. The angles we can obtain from the information given in the question, and we can finally calculate the MR values for each of our blades. Okay, exercise 3I there. Okay, exercise 3I, there's a suggested table you would use. Okay, exercise 3I, then there's my MR force values if you want to compare yours with mine. Horizontal components MR cos theta as always. And this summates to be negative this time, so be a bit more careful with that one. And my MR sin theta values for the vertical components summates to be negative J0.063. So this is where you've got to be careful. Now the phasor or the vector you're considering is down here. Alright, so very careful. You get the direction right. It's negative on the horizontal. So negative 0.0076. And it's also negative in the vertical, negative 0.063. So we're in the third quadrant of the Argan diagram. So when you're working out the out of balance using Pythagoras theorem, nothing changes there. That's fine. That's going to be the same as previously, but the angle's different. You need to be careful with the angle. Always positive from here. So in this case, you're going to work out this angle in here using your trig. I've actually called that angle beta, notice. All right, so I'm just give it a label, called it beta. So I'm working out the resultant angle beta here using the trig function, the arctan function here. So that's the out of balance angle, 83 degrees. But we must dimension it from the origin shown up here. So we need to add to that the 180. So do be careful that you draw your vector diagrams or your Argan diagrams, you get the correct quadrant, and then you work out the appropriate angle. So 263 degrees, or if you wanted to, you could have negative 97 degrees, but 260 degrees in the anti-clockwise direction from the origin shown. And then to work out the actual balance mass required, because that's what the question wants you to find here, you've got the balance radius of 0.3 meters. You can go back to our equation, M balance is equal to the MR out of balance divided by the radius of the balance mass. And you can evaluate that. I get 0.212 kilograms. The balance mass has to be in this orientation. Right, so that's where we get the 83 degrees from here. So do be careful of those quadrants and where the out of balance phasor is. okay, because your balance mass, balance force has to be equal and opposite to it. So in this case, the angle that we calculated, theta, is 83 degrees, and that's the angle there, 83 degrees. Have a look at exercise 4i as a bit of enrichment, okay? And this is interesting because in this case, you're drilling holes in the flywheel. So you consider that as a negative mass if you want to in your calculations. But you think that through. Slightly different concept to the actual solutions, identical to what you've been doing. There's no different than that. But the actual question there, exercise there, is more thinking about it, getting information out of the question. You're actually drilling holes this time, so you can have negative masses. And also exercise 5, I'd like you to have an attempt at. It talks about 400 blades, but fear not. If you read the question carefully, extract the information carefully, you will not be analysing 400 blades. Right? So that's not going to happen. But you do need to think through the question, how it's worded, how many blades do you actually need to analyse in that particular question. So I'm going to leave that one with you as well. If you can have a go at those two for me. Cheers, guys. See you later on. Bye-bye.